Welcome to the first in a two-part series of lectures dealing specifically with chemistry that is important for understanding biological principles. As I mentioned in one of our first lectures, one of the things we need to do in a cell biology course is talk about the building blocks necessary for cellular life. And those building blocks are going to start with some basic chemistry. Hopefully most of this will be a review for all of you, but if it's not, this is a really good time to learn some basic fundamental chemistry or chemical aspects. So then, starting with the very basics, the first thing I want to state is that all organisms are made up of matter. Matter is anything that occupies space and has mass. It's found on Earth in three distinct physical states: solid, liquid, and gas. Now, matter is composed of chemical elements. Elements are substances that cannot be broken down into other substances. The elements got their name from the ancient Greeks. The ancient Greeks focused on air, water, fire, and earth as the classic elements of life. They thought that all of these substances were made, the elements that we're going to be talking about in this lecture, were basically made by blending the different components of air, water, fire, and earth. Now, we know that not to be the case. However, this is historically how the elements got their generalized name. What you see on this particular slide are some classic examples of elements, and what we're going to do is take a deeper look at elements and atoms in order to understand, again, some basic chemical principles. Now, elements consist of one kind of atom, and an atom is defined as the smallest unit of matter that still retains the properties of an element. When we look at atomic structure, we can break that down even a little bit more, and this is going to be important in understanding, again, some of the concepts that we're going to get to in today's lecture. So each atom can be divided into what's known as subatomic particles. What you have at the center of an atom is a dense nucleus made up of particles known as neutrons and protons. Neutrons are neutral in charge, and protons are positive in charge. And again, these two subatomic particles make up the center or the dense nucleus of an atom. In addition to that, there's one other type of subatomic particle known as an electron, and an electron has a negative charge associated with it. When you have an atom, what you have in the diagram that you see here is two different versions or depictions of an atom. Imagine an atom in the shape of a sphere, and at the very center of the sphere would be the nucleus where the protons and the neutrons are found. The electrons circle that dense nucleus around, again, the nucleus, to create what's known as a cloud of negative charge or electrons. So again, we can't necessarily see that three-dimensional shape, but you can hopefully visualize the three-dimensional shape. And then lastly, what holds all of these components together, the separate subatomic particles of an atom, is electrostatic interactions. That is, the positive charge from the protons and the negative charge from the electrons attract one another, positive and negative attraction, and that is what holds all of the components of the atom together. Now, each of the elements that I mentioned in the previous slide differ from one another in the number of subatomic particles in their atoms. That is, it is the composition of the atom that differentiates elements from one another. There are some additional characteristics or features that you should be familiar with when we talk about elements, and that is the number of protons in the nucleus of an atom dictates what's known as the atomic number. An atom's mass number, also referred to as its atomic weight, is the sum of the number of protons and neutrons. And then lastly, the mass is a measure of the amount of matter in an object. Now, all atoms of the same element have the same number of protons associated with them. So let's look at this table. In fact, we'll look at the very first column dealing with carbon-12. And unless otherwise noted, atoms are neutral in charge. That means that they should have the same number of protons and the same number of electrons. But again, there are some exceptions to that, and I'll get to that in just a minute. But let's look again at this first column with carbon-12. What you can see is that carbon-12 has 6 protons and 6 neutrons. So going back to the definitions that I included on this particular slide, the atomic number is the number of protons in the nucleus. So for carbon, the number of protons is 6, therefore its atomic number is 6. We also included the definition of the mass number, or the atomic weight, and that is the number of protons plus the number of neutrons in a nucleus of an atom. And in this case, they are both 6 protons and 6 neutrons for a total of 12, which is then the atomic weight, or the mass number of carbon. Now, there are some exemptions to this balance that I just talked about, and that is what we define as an isotope. An isotope is any of several forms of an element that have the same number of protons. Again, it's the number of protons that dictates what the element is, but has differences in the number of neutrons. So if you look at this table once again, you can see that we actually have 2 distinct isotopes, carbon-13 and carbon-14 of carbon. Carbon-13 and carbon-14, just like carbon-12, all have 6 protons. And again, it is these 6 protons that is the defining characteristic or feature that notes this as carbon. What's different in these isotopes, carbon-13 and carbon-14, is the number of neutrons that you find in the nucleus of the atom. Carbon-13 has a total of 7 neutrons rather than 6, and carbon-14 has a total of 8 neutrons, again, rather than 6. So based on the definition, again, of mass number or atomic weight, if we add the number of protons and neutrons together, that gives us the mass number. So for carbon-13, the mass number is 13, and for carbon-14, the mass number is 14. And again, sort of as a rule of thumb, in most cases, the number of protons is going to be equivalent to the number of electrons. And you can see that that hasn't changed here with carbon. But we will see some exceptions to that a few slides down the road here. One other thing I want to mention with this particular slide is to highlight hydrogen. Hydrogen is a very special type of element in that it consists of only a proton and an electron. There is no neutron in the nucleus of the hydrogen atom, and this gives hydrogen some different characteristics or properties in its chemical behavior, and we're going to get to that as well. But I just want to highlight this here, and I want you to refer back to it when I mention it again. Hydrogen, again, is a special type of atom in that it does not have a neutron in the nucleus of its atom. Now what you see here is what's known as the periodic table of elements, and it is a list or a compilation of the elements that we know exist on Earth. There are 92 elements that have been identified in nature, and they are organized by atomic number in this particular table, as well as by their electron configuration. That is, the way that their electrons are organized around that nucleus of each of these atoms is another way that this table is actually organized. So tying the elements back into a biological perspective, there are 25 elements that are essential to life, meaning that they are required in order for organisms to remain alive and survive. 4 of those elements make up about 96% of the weight of a human body and actually just about any other type of organism in question, or most living organisms. Those top 4 elements are oxygen, carbon, hydrogen, and nitrogen. So again, 25 elements are considered essential, and 4 of those 25 make up the majority of the weight found in a typical living organism. On the right-hand side, you can see a list of those elements that I've just highlighted for you as far as the essential elements. You can see the top 4. In the next bracket down, you can see by percentage additional elements that are in fact important for life. And then lastly, in the bottom bracket, you can see what's referred to as the trace elements. And these are ones that are found in less than 0.01% of a living organism. Now what I want to do is talk a little bit more about electrons, because electrons, specifically the number and the configuration of those electrons, determine how an atom behaves when it encounters or interacts with other types of atoms. Some of the first things we have to discuss is that electrons exist at fixed levels or energy states, also referred to as electron shells. The very first energy level or energy shell can hold a maximum of 2 electrons. The next energy level, moving away from the center or the nucleus of the atom, can hold a maximum of 8 electrons. The third energy level or energy state or energy shell can also hold a maximum of 8 electrons. And these energy shells, again, move away from the nucleus of the atom. So the first one is the closest to the nucleus of the atom. The second level is further away from the nucleus of the atom. And then the third level is further away than either of the first 2. So to recap briefly, the first energy state or electron shell can hold a maximum of 2 electrons. The second energy shell or electron shell can hold a maximum of 8 electrons. And the third energy level or energy shell or electron shell can also hold a maximum of 8 electrons. Now, another thing about electrons is that electrons occur in pairs. That is the most stable organization for electrons is when they occur in pairs, so 2 electrons together. And that's going to become important as we continue talking about these interactions between atoms coming up here next. So what you see on this particular diagram is the 4 elements that hopefully you recognize from the previous slide as the top 4 of our essential elements: hydrogen, carbon, nitrogen, and oxygen. What I want to do is highlight these just a little bit because, again, they are the top 4 essential elements and they do play a really big role in biological chemistry. So the first one, hydrogen, like I highlighted previously a few slides back, hydrogen is a very interesting type of atom in that it does not have a neutron in its nucleus. It consists of 1 proton and 1 electron. Hydrogen is abbreviated by the letter H, and its atomic number is 1, because again, the atomic number represents the number of protons associated with the atom in question. In this case, hydrogen, because it only has 1 proton and 1 electron, again, will have some additional chemical behaviors that we will get to in just a little bit. But what you can highlight also with this particular element is the representation of that first energy shell or energy state that I was mentioning. What you see in this figure is the representation of the 1 electron and then a circle, meaning an empty space, for a second electron that could complete this energy shell. Remember, this energy shell can hold a maximum of 2 electrons, and there's only 1 in this particular case for hydrogen. So the next one, or the next element, is carbon. Carbon is designated with a capital letter C. Its atomic number is 6, which again represents the number of protons found in the nucleus of this particular atom. In normal circumstances, and in most cases, the number of protons is going to be equivalent to the number of electrons. So what you see in this representation in this diagram are the 6 electrons that are present circling the nucleus of the carbon atom. The first energy state, or energy shell, or electron shell, has the maximum of 2 electrons, and you can see that in this figure. The next energy state, or electron shell, has a total of 4 plus 2, giving us the 6 electrons total. But what you can see is that the orientation of these electrons is a little bit different in that there are empty spaces in each one of the potential pairs of electrons. And this is going to become important because of carbon's reactive nature due to this electron configuration. And we'll come back to that, not in our next lecture, but the one after that. The next element in this figure is nitrogen. Nitrogen is indicated by the capital letter N. Its atomic number is 7, which again represents the fact that there are 7 protons in the nucleus of this particular atom. 7 protons and 7 electrons, and again you can see that electron configuration with the diagram denoted here. Lastly, we have oxygen, whose atomic number is 8, which means that there are 8 protons in the nucleus of the oxygen atom. In addition to that, there are then only 8 electrons that circle the nucleus, and you can also see that electron configuration pattern in this particular figure. Also, oxygen is denoted with the capital letter O. Now, the electrons of a given atom vary in the amount of energy they possess. So what we need to do now is go back and define really what energy is. And energy is defined as the ability to do work. One form of energy is referred to as potential energy, and this is the energy that is stored due to position or location. And this concept is going to become important again when we talk about electrons and the amount of energy that they possess. And this is going to differ depending upon the location of the electron. And I'm going to get to that here with this particular slide. As I mentioned previously, electrons exist at fixed energy levels, energy states, or electron shells. This is terminology that I used in the last lecture, or excuse me, in the last slide. Electrons of an atom have potential energy due to their position relative to the nucleus. The closer an electron is to the nucleus, the stronger the interaction between those positively charged protons and the negatively charged electron is going to be. So there's going to be a nice, strong interaction with electrons that are closer to the nucleus of an atom compared to electrons that are further away from the nucleus of the atom. While there is still electrostatic interaction, meaning positive and negative charges attracting one another that hold the atom all together, these electrons that are further away are not going to be held as tightly or in strong association with the nucleus. Okay, again, it's because the distance is greater, so the ability to hold those electrons in is going to be less. So the more distant an electron is from the nucleus, it will actually have greater potential energy. Okay, why is that? There's a not as strong interaction between electrons that are further away from the nucleus compared to those that are really close to the nucleus. The ones that are further away have the ability to break away from the nucleus because that interaction is less strong. Because they could potentially break away or move away from the nucleus of an atom, that gives them a great deal of potential energy. And again, it is this distribution of electrons that determines the chemical behavior of a given atom. Let's focus on the bottom figure of this particular slide. On the bottom figure of this slide, you have a diagram that represents the the element known as neon. Neon has an atomic number of 10, which again, the atomic number represents the number of protons. But because we know the number of protons, we can extrapolate the number of electrons we would expect, which would then also be 10. Looking at the far left-hand figure in this diagram, you can see the first energy shell depicted, and it is full or complete with 2 electrons. That's in panel A. Panel B, you can see this is the second energy shell or energy state, and it is filled with the maximum number of electrons, which is 8. So 8 in the second energy shell, 2 in the first energy shell is the complete number of electrons that we would find associated with this particular atom. In panel C, you can see it all put together with all 10 of those electrons depicted in this figure, and this is referred to as an electron shell diagram. Neon, because it has all of its electron shells filled, that is, the first one is completely full, the second one is completely full, makes it very boring from a chemical perspective, in that these electrons are in pairs, the energy shells are complete, and now you have very little movement or leeway for interaction with other types of atoms because it is very stable in this configuration. Don't worry so much about the figure at the bottom half of that diagram. This just represents how the electrons are found, and for our purposes, the patterns that the electrons travel in is really not as important. It's just understanding the energy shells themselves and filling those energy shells or not filling those energy shells and what that means for chemical behavior. So in this case, because those energy shells or electron shells are completely filled, neon is going to be non-reactive. It's not going to interact with other types of atoms. Let's compare that with something like carbon. Carbon has atomic number of 6, which again means there's 6 protons in the nucleus, and we can extrapolate from that there are 6 electrons that surround that nucleus. If there are a total of 6 electrons, the first energy shell is filled with 2, and there are then 4 electrons in the second energy shell. Because electrons would like to occur in pairs, there is the potential for interaction with other electrons in this outermost shell. The outermost shell is referred to as the valence shell, and again, because this valence shell, so just to recap, as I stated in the last slide, the chemical behavior of an atom is going to depend on the number of electrons in the outermost shell, the valence electrons. If you have a complete valence shell, like the neon example we just looked at, that atom is going to be unreactive. But if the valence shell is not complete, this is where we then have the potential for interaction with other atoms. Atoms with incomplete valence shells can interact with other atoms and form chemical bonds. The first type of chemical bond that I want to talk about is known as a covalent bond. And a covalent bond is one where there is a sharing of a pair of valence electrons by 2 atoms. Remember, electrons would like to occur in pairs. That would be the most stable configuration for those electrons in that shell. So, a covalent bond is going to be the sharing of a pair of electrons by 2 atoms. This then gives us one more definition that I'd like to add at this point, and that is that of a molecule. A molecule is 2 or more atoms held together by a covalent bond or covalent bonds. All right, so let's look at the figure that you see on this particular slide. This figure has a lot of information in it that I'm going to go through, and that is there are the electron configurations of these molecules that you see in the first column. We'll talk about that in just a minute. you have what's known as the structural formula. This gives you some indication of how the atoms interact with what type of bonds are present. Typically, the single line designation indicates a covalent bond. You have also a space-filling model in the next column and the ball and stick model in the final column, just to give you some different views of what these molecules can be represented as or how they might look. So the first molecule in question is hydrogen gas, and hydrogen gas, also depicted on here, is the molecular formula. What you see here is the letter H, which is the symbol that represents hydrogen, and the subscript 2, which means there are 2 hydrogen atoms in this molecule. That is the molecular formula. The electron configuration is really important because this very clearly depicts what's happening in a covalent bond. You have one hydrogen atom with its 1 electron in its outermost shell. You have the second hydrogen atom with its 1 electron in its outermost shell. Because electrons would like to occur in pairs, there is an attraction of these 2 atoms towards one another, so that the interaction between the electrons allows for the atoms to basically be held together, in that both of these atoms are now sharing this pair of electrons. The best way to describe this, and I usually do in our face-to-face version of the class, is if I was standing up and I had a ball in my hand, whatever kind of ball you want to have, basketball, and my daughter was standing in front of me, facing me with her basketball. This would represent 2 hydrogen atoms, the basketball representing the electron of each of those hydrogen atoms. If she and I began to toss the ball back and forth to each other, I toss mine to her, she tosses hers to me, and we do this back and forth and back and forth and back and forth and back and forth, is exactly what is happening in a covalent bond between 2 hydrogen atoms. Those electrons are going around each of the nuclei of the atoms. They are being shared, and so this is what allows for that interaction to take place. So that's the heart of what's happening in a covalent bond. You can also have a double covalent bond, like you see with the oxygen gas molecule in the next row. Here, a double covalent bond just simply means you're now sharing 2 pairs of electrons, and that double covalent bond is indicated by the 2 straight lines between the atoms overall, like you see in the figure. Lastly, you have a little more complex example where you have different types of atoms coming together to form a molecule. In this case, this is methane, 1 carbon, 4 hydrogens. Carbon, because of its unique electron configuration, has the ability to make 4 covalent bonds, and that's what's happening in this particular figure. The next type of bond I want to discuss is an ionic bond. An ionic bond forms when you have oppositely charged atoms interacting or attracting one another. Charged atoms are referred to as ions and can be further subdivided into cations, which have a positive charge associated with them, and anions, which have a negative charge associated with them. So let's look at the left-hand side of this figure, looking at the sodium atom first and then the chlorine atom second. The sodium atom has an atomic number of 11, which means it has 11 protons, but for our purposes it means it also has 11 electrons. That means the outermost shell has only 1 electron in it. The other shells are filled with electrons, and the outermost shell has 1 electron in it. Chlorine, on the other hand, has an atomic number of 17, which means then that there are 7 electrons in the outermost shell. There is space for 1 additional electron to make chlorine much more stable. So what happens in this interaction between sodium and chloride or chlorine is that the one electron that's in the outermost shell of sodium is stripped or stolen by the chlorine atom to fill the chlorine atom's outermost shell. In this case, we now have generated ions. We have sodium ion, which has a net positive charge because it has one less electron than it's supposed to. We have the chlorine ion that has a net negative charge because it has one more electron than it should have. Both of these ions are much more stable than the original atoms that we've described on the left-hand side, because in both cases you have complete outer shells, which makes them much more stable. But because they are much more stable and their outermost shells are complete, they have net charges. And it is the attraction between the positively charged sodium and the negatively charged chlorine that holds sodium chloride together in an ionic bond, like you see in this example. The last type of bond that I want to talk about is a hydrogen bond. But before we can talk about how hydrogen bonds form, I'm going to talk a little bit about the molecular structure of water. We will discuss water and the properties of water in the next lecture in a lot more detail, so we're setting the stage for that lecture, but again, we're also utilizing this information to understand how hydrogen bonds form. In this figure, you have what is known or represents a water molecule. Water is made up of 2 hydrogen atoms and 1 oxygen atom. The hydrogens are covalently bound to the oxygen. Now, in many circumstances, a covalent bond where the electrons are shared equally is referred to as a non-polar covalent bond. However, in some circumstances in a covalent bond, the electrons are not shared equally. The electron may spend more time around the nucleus of one atom compared to the other atom in the covalent bond. This is what happens with water. Specifically, the electrons that are part of the hydrogen atom tend to spend more time around the oxygen atom than they do around the hydrogen atom. In this case, you have what is referred to as a polar covalent bond. It's an unequal sharing of electrons. The electrons spend more time around oxygen than they do around hydrogen. This makes the molecule itself a polar molecule, meaning that there are portions of the molecule that have a slightly negative charge associated with them. That's the region around the oxygen, because those electrons are spending more time around oxygen. There are also portions that have a slightly positive charge associated with them. That's the portion around the hydrogens. That's because, again, those electrons are spending less time around the hydrogen atom. When you have molecules that have polar covalent bonds, this is what allows for hydrogen bonds to form. Hydrogen bonds form between molecules that have polar covalent bonds. So in this example, you see water molecules interacting with one another. More specifically, the net negative portion of one water molecule is being attracted to the net positive portion of another water molecule. And this is what allows for these water molecules to interact with one another via hydrogen bonding.